On August 23rd, India created history when Chandrayaan 3 made a successful touchdown on the moon's south pole. With this, India became the first nation to make a soft landing on the south pole. Chandrayaan 3's rover Pragyan has already started exploring the lunar surface and sending incredible scientific data which Isro is sharing with the world. But there are even more exciting missions that India planned for the future, and one of them is Aditya L1 that was just launched on 2nd September in the morning 11:20 IST. This one is solely dedicated to study our sun, the nearest star from our planet. Aditya L1 spacecraft is India's first observatory class satellite that will study our sun from a specific distance and point in space known as the Lagrange Point 1. Derived from Sanskrit word Aditya, it means the sun, and L1 in our mission name represent a specific point, region, or you can say a place where the net gravitational pull between the sun and our planet Earth becomes almost zero, which means that with a very little fuel and positioning of a satellite or telescope or a spacecraft, you can stay there for a longer period of time, gather your scientific data with much better accuracy while maintaining a constant flow of communication and spending less fuel. But why do we even need to launch an entire satellite to study our sun, you may ask? We know that for distant stars and galaxies, we need to avoid our atmosphere that absorbs and interferes with photons traveling billions of light years from who knows since when. However, our sun is right there, right? The brightest star, the source of life on Earth. We could easily study it from Earth, right? Well, somewhat, but no. Our Earth has an invisible shield that protects us from harmful solar winds that contain high energy photons and particles, and even protects us from cosmic radiations. In addition, the ozone layer absorbs the majority of UV rays from our sun and protects the delicate DNA structure on Earth. Well, this is awesome, right? An invisible shield which we call as the magnetosphere, protecting us from high energy solar winds. But it's the same thing that somewhat limits our ability to study our own stars' properties and behavior in detail. So to avoid this, we need to get out of the Earth's gravitational sphere of influence and make accurate observations. Our sun is a huge ball of plasma and gases, where hydrogen is constantly compressed and fused due to gravity, which in turn releases a huge amount of energy equivalent to billions of hydrogen bombs going off each second. This in turn creates the pressure at the center that pushes against the gravity and keeps a star balanced. The center of our sun is around 15.7 million degrees and tumbles down to approximately 5 to 6,000 degrees on the surface. However, the corona, no, not this corona, is the outermost part of the sun's atmosphere, usually hidden by the bright light of the sun's surface at a whopping 1.5 to 2 million degrees. We call it the corona heating problem. We don't know why it's so hot, and the sad part is that it's hidden under the bright light of the sun. Well, you can see it, but only for a short span during the solar eclipse, and that too when a total solar eclipse happens and the moon completely covers the sun. So to avoid any interruption, we must look at our star directly and conduct studies without any interruption. Also, we know that solar winds contain highly charged particles that can easily damage modern electronics, thus destroying modern infrastructure if one hits the Earth. We can detect it and take some measures to protect our infrastructures, as these solar winds, although travel at a very high speed, they do not reach near the speed of light. However, there are still many questions related to our sun's atmosphere, magnetic fields, solar wind patterns, and more that need to be answered. Well, now that you know the reason behind launching a spacecraft to study our sun, let's understand the Lagrange points and learn more about Aditya L1 mission. A Lagrange point or points are the small regions in between and around two or more spherical bodies where the gravitational pull towards them becomes equal to the centripetal force. These points in space can be used by a spacecraft to reduce fuel consumptions needed to remain in position. L2 and L3 lie beyond the side of our sun and the Earth, so we are only left with L1, which lies at a distance of 1.5 billion kilometers from Earth. With little maneuvers, our satellite can easily orbit in a short, fixed pattern and observe the sun uninterruptedly. Now let's see how Aditya L1 will reach its destination, the Lagrange Point 1. Similar to Chandrayaan 3, Aditya L1 will stay put in earthbound orbit, where it will gradually gain the necessary velocity for its future journey. This will take around 16 days. After 5 of these Earth-centered orbit transfers, and at the 5th revolution, it will fire its propellers and move out of the Earth's sphere of influence, meaning it will now be free from Earth's gravitational pull. After this, Aditya will be in what we call the cruising phase for almost 110 days, where its LM engine of 440 newtons will take Aditya L1 to Lagrange orbit insertion point. After that, a series of small maneuvers using smaller thrusters of around 22 newtons will push Aditya into the orbit of Lagrange point. Yes, it's not a single point, rather than it's an imaginary point on which the satellite or spacecraft orbits around and keeps very stable position. And there it will get an unobstructed view of the sun for years to come with minimal fuel usage. At around 126th day, Aditya will finally reach its destination point and start making its observations. So let's see what payloads are on board Aditya L1, with 4 of them carrying our remote sensing of the sun and 3 of them carrying in situ observations. The 4 sensing payloads consist Visible Emission Line Coronagraph or VELC. Normally, due to the brightness of our sun, we are not able to see the sun properly, but if it's blocked like it does in the total solar eclipses, then the corona is visible. So that's what VELC is going to do. It will create an artificial eclipse that's going to help Aditya study the outer corona. VELC is capable of studying our sun in both visible and infrared wavelengths. It's going to help us answer questions like why the corona is so hot, how and where the coronal mass ejections occur, and what is the relation between corona's temperature and the sun's magnetic field. Second one is Solar Ultraviolet Imaging Telescope or SUT, that will image the solar disk in near ultraviolet wavelengths ranging from 200 to 400 nanometers. We never studied our sun in this wavelength, and Aditya will constantly film it and help us understand the behavior of different parts of the sun. Third one is the Solar Low Energy X-ray Spectrometer or SOLEX. This soft X-ray spectrometer is designed to measure the solar soft X-ray flux in order to study the solar flares. It's going to play a key role in understanding the role of X-rays coming from corona, thus providing whether X-rays are somehow responsible for corona's unusually high temperatures. Fourth one is our High Energy L1 Orbiting X-ray Spectrometer or HEL1OS. It will study the dynamics of the sun's atmosphere, especially corona, how much energy is required to accelerate solar particles at such a high speed during solar winds and coronal mass ejections, and how much energy is concentrated in a single place. The remaining 3 are in situ payloads and consist ASPECS or Aditya Solar Wind Particle Experiment. ASPECS have 2 subsystems, SWIS or Solar Wind Ion Spectrometer. It's a low energy spectrometer designed to measure the protons and alpha particles of the solar wind. The second subsystem is STEPS or Suprathermal and Energetic Particle Spectrometer. This is a high energy spectrometer designed to measure high energy ions in the solar wind. ASPECS will study different particles ejected by the sun in the form of solar winds and gather more information about them. Second or sixth one is Plasma Analyzer Package for Aditya or PAPA. PAPA is designed to study the composition of energy levels of the solar winds. It will also perform mass analysis and find out how and in what concentrations the ions are distributed in solar winds. And the last one is Advanced Triaxial High Resolution Digital Magnetometer. As the name suggests, it will measure the low-intensity interplanetary magnetic fields in space. This will help us understand the sun's changing magnetic field and how it impacts our solar system. It has 2 sets of magnetic sensors, one on the tip of a 6-meter deployable boom and the other one in the middle of the boom around 3 meters away from the spacecraft. These 2 sensors placed at 3-meter distance will help us understand the change in magnetic field by measuring the change in voltage between two sensors caused by the changing magnetic field. All in all, Aditya L1 is packing it, and it's going to play a very important role in finding the answers to some fundamental questions about the Sun and our solar system. Aditya L1 is going to expand our horizon about the knowledge we have about our stars, solar system, and even the universe. If you like this video, please give it a big thumbs up and share it with others too. Also, if you have any suggestions for me, like how I can improve the content or any topic you want me to make a video, then please mention them in the comment section below. And don't forget to hit the subscribe button and give a follow me on Instagram. I'll be back soon with a new video. Thank you.